Welcome back. You have come to the last two steps in the planning process. Prove process capability and implement the plan. Implement the plan includes a transfer of responsibility from the planners to the operating managers. These managers will balk at accepting responsibility for results if the process can't do its intended job, if it lacks process capability. That's why this session begins with proving process capability.
Operating managers will trust a process whose capability has been proven by results, by meeting the quality goals under operating conditions. In cases where such direct methods are not feasible, we must use acceptable alternatives. Let's examine a few of these. The dry run is a test of the process under conditions which approximate operating conditions. The purpose is to test the process. The resulting product is not sent on to customers.
A data processing manager purchased computer software designed to replace a card-oriented data system with a tape-oriented system. She tested the software by running the same input data through both systems and then comparing the results.
In manufacturing processes, it is common practice to conduct tool tryouts. The aim is to produce enough units of product to demonstrate that the tools can meet quality standards under operating conditions. Pilot testing is an intermediate scaling up between the planning phase and full-scale operations. The approach goes by various names. A test town for trying out a new marketing plan. A pilot lot for testing out a manufacturing process. A test department for trying a new managerial concept. The results of such tests are used for decision-making to decide whether to go to full-scale operation. For such an important decision, it is necessary to define in advance the questions to which answers are needed and to design the data collection plan accordingly. Direct measurement of process capability is based on data collected under operating conditions. But the dry run and pilot testing provide only an approximation of process capability, since the conditions only approximate operating conditions. Another approach to evaluating process capability is simulation of the process. Simulation literally means an imitation of the real thing. The planning may contemplate a new process which involves considerable investment. Since the process is new, such an investment is at risk. There's no proof that the process will be able to meet the quality goals under operating conditions. However, simulation can reduce the risk. One can design a scaled-down process, test it out, and then use the test results to estimate what will be the results under full-scale operation. The armed forces stage maneuvers to test out operational readiness. The workforce in an office building holds fire drills. The theater troupe conducts rehearsals. Now, computer-aided design makes it possible to design and test mathematical representations of models without even creating a physical model. A special form of simulation is through mathematical models which deal with symbols rather than with physical things. Consider the case of the Space Shuttle arm, the device which enables the Space Shuttle crew to capture or deploy massive objects in space. The process of handling those massive objects depends critically on the proper functioning of the arm. How can the process capability of the arm in zero gravity be proved on Earth, which has a gravity environment? A carefully designed simulation can answer many important questions relative to process capability. With availability of computer-based tools of ever greater sophistication, designers are coming to rely more and more on mathematical simulation as a means of gaining precision and saving time, especially in the early stages of design.
Simulation is a tool of great value provided we understand the limitations and risks. We can better understand these limitations and risks by noting that simulation and full-scale operation are carried out in two different worlds. The world of the laboratory and the real world of operations. Simulation permits evaluating process capability in the laboratory and then extrapolating to predict process capability in operations. We've already pointed out that these worlds differ greatly and that operations planned on the basis of laboratory results can cause trouble. And yet, in some circumstances, planners must make do with process capability estimates made under laboratory conditions. Using imperfect estimates makes it all the more important that extrapolation from laboratory findings be based on inputs from both worlds. Such inputs can be acquired through team efforts, joint planning, and design review.
In many cases, quality planners evaluate process capability only to discover that the process is not capable of meeting the goals. We have plenty of experience with incapable processes. Our former ways of quality planning created a lot of such incapability, often without our knowing it. We learned of the existence of the incapability only when operations got underway. Each such case then became a crisis or a chronic source of quality troubles. By learning about such incapability during the planning stages, we enlarge our range of choice. We create multiple options to avoid burdening the operating forces with an incapable process. One option is to analyze the extent of incapability. The process may be capable as to some goals, but not as to others. Such analysis identifies the incapable residue and thereby narrows the problem. Another option is to improve process capability by carrying out a quality improvement project. Such a project requires digging deeper to quantify the relationships between process variables and product results. In tackling such projects, we should concentrate on the dominant variables in order to simplify the analysis. Still another option is to review the product goals to see if the optimum is best served by revising the product goals. The traditional approach to an incapable process has been to endure the incapability and the resulting chronic waste. In that event, it has also been necessary to provide for an adequate level of customer service for both external and internal customers. Enduring the incapability should always be regarded as a temporary measure. Future planning projects, as well as the annual improvement process, should keep reviewing such cases. When the planning team transfers the quality plan to operations, it also transfers responsibility for control. The operating forces become responsible not only for producing the product, but also for maintaining the process at its planned level of capability. This control is exercised by use of the feedback loop, by evaluating actual performance, comparing actual to goals, and taking action on the difference. All this implies that the process is controllable, that the planning has provided the means for carrying out the activities within the feedback loop. For many processes, the planning of the control system is left to the operating forces. In such cases, planning for control should not wait until the transfer to operations has been made. Instead, the planning for control should be done as the process planning proceeds. Otherwise, the risk is that the process will lack controllability under the full range of operating conditions, and that discovery of this fact will come too late in the day. Our experience has been that such cases involve costly retroactive revisions. Now let's turn to the process of transferring the plan to operations. The planning work is complete. but the work of the planners is not. During process planning, the planners acquire a great deal of know-how about the process. The planners should transfer that same know-how to the operating forces. There are various ways of making this transfer. Process specifications define the process and set out the goals to be met. This information is vital to the operating forces, but it is the barest minimum. Procedures are a welcome elaboration. They can include instructions, cautions, the why as well as the how. Being in writing, these procedures become a reference base and an aid to the training of new employees. Briefings are meetings specifically set up for transfer of information. When well organized, these briefings are most useful. The planners make a presentation built around a written statement and supplemented by visual aids. Questions and discussion are encouraged so that the transfer goes beyond the surface. On-the-job training is another means of transferring know-how. In many cases, the planners can usefully participate in the training given to the operating supervisors and the workforce. The merits of this approach go beyond the transfer of know-how. There is an associated valuable feedback to the planners. The supplier learns from the customers. Formal training courses are needed in those cases where the new process departs radically from the past. Such formal training courses become essential if the new process is to be applied widely throughout the organization. Prior participation by those who will be impacted is the most timely form of transfer of know-how. All of the other forms are a mixture of transfer of know-how before the fact and after the fact. Both forms are needed, but the greatest damage is done by failure to transfer know-how before the fact, especially through prior participation. Such failure ignores the benefits of early warning and of the teamwork which results from prior participation. In some companies, transfer of the process from planning to operations is structured and formalized. An information package is prepared consisting of certain standardized essentials, goals to be met, facilities to be used, procedures to be followed, instructions, cautions. The package is accompanied by a formal letter of transfer of responsibility. In some companies, this transfer takes place in a near ceremonial atmosphere. In other companies, formality is minimal. The structured approach has value. It tends to evolve checklists and countdowns which assure that the transfer is orderly and complete. Formality is useful if it contributes to such orderliness and completeness. In companies which already have such a structured approach, the planners need only to adapt the project information package so as to conform with established practice. If the company has a loose structure, or none at all, the planners must make their own decisions on what to put into the information package and on how far to go with formalities.
Process planning is aided by access to data on process capability. Transfer to operations should include proof that the process can do its intended job under operating conditions. In the absence of means to prove process capability by direct measurement, planners may resort to dry runs, pilot tests, simulation. Simulation may include the use of mathematical models. The world of simulation differs extensively from the world of full-scale operation. Extrapolation from simulated processes into full-scale processes requires inputs from both worlds. Discovery of process incapability during the planning stages is better than discovering it after operations begin. Early discovery increases the range of options available for dealing with such incapability. The planners should transfer the know-how gained during the planning process. Means for transferring this know-how include process specifications, procedures, briefings, on-the-job training, formal training courses, and prior participation. Transfer from planning to operations is best done through a structured approach.
It's now appropriate to summarize the high points of this entire series of videocassettes on quality planning. Managing for quality involves three processes: quality planning, quality control, and quality improvement. In the past, quality planning has been inadequate, making it a hatchery for new quality problems. Effective quality planning follows a universal sequence of steps. Identify customers, discover customer needs, translate those needs into your language, develop units of measure, develop means of measuring, develop product features to satisfy the customer needs, optimize goals for the product features, develop a process to create the product features, optimize goals for the process features, prove that the process is capable of meeting the goals, and transfer the plan to the operating forces for implementation. The key ingredients of this universal sequence are: it's a systematic approach, it focuses on the needs of customers, and it is characterized by collaboration between customer and supplier throughout the planning cycle. The purpose of this series of videocassettes has been to help you and your company improve quality planning through understanding the concepts which underlie effective quality planning and applying the concepts to a planning project of your own. We hope that this application will stimulate you to take more and more such applications. That's the way you and your company will acquire greater and greater mastery of the quality planning process and shut down the hatchery for good. So long and good luck.